Okay, hi everyone. So today we're going to be starting this contest pretty late, and that's because uh, I had a power cut at my house, so I was not going to do this contest at all. But now I have the power back. By the way, there was a power cut, and my laptop battery was also very less. Yeah. Anyway, now we can start doing these questions. There are already thousands of submissions here. And I have this dark theme because I figured that most of the people who watch my videos um, watch it at night in a dark room or something, so it would hurt their eyes. That's why I got my drawing board to be dark, and this CF also dark. So yeah, everything is dark now. Okay, anyway, so we're at this problem A right now, the first problem, and we're starting 15 minutes late. So you have two positive integers A and B. You can perform two kinds of operations. Uh, Either you can divide B or you can add 1 to B. Okay, and you want the minimum number of operations to make A equals 0. Okay, so I think if even if B is 2, so like if B is 1, it is impossible. So we have to make B at least 2. So even if B is 2, then I think there won't be more than 30 operations, I think, log of like which is just the log of A, right? And if B is 3, then there might be very less operations. I think there's no point of getting B greater than 32 or something, or there's no point increasing B more than 32 times or something like that, probably. Yeah, so we can do something like that, I think. Okay, so we take this T and we take this A and B. Okay, sorry, right? And let's say answer equal to 40 or something. Like it will always be smaller than 40. So we will definitely find something that is smaller than that. But yeah, so okay. So we can start a loop from 0 till 32 maybe. Okay, and we will add 0 till 31. So we will add I to B. Okay, so yeah. Now if your B plus I equals 1, then we will continue because this will never give us an answer. Otherwise, we just want to see how many times we can divide B plus I from A and not get 0. Okay, let's say count equals 0 while while A, sorry, we need a temp as well. Let's say temp equals A. Okay, and while temp is not equal to 0, we can do something like count plus plus and temp equal to temp divided by B plus I. Okay, something like this. So the total number of moves here are sorry, we want the minimum. Okay, so the total number of moves here are, first of all, we did I moves of increasing B, and then we did count moves to make A 0. Okay, and I think that's the answer. Let's see. Okay, so we got the correct answer on the first test case. Green means correct. I don't have to check whether all the values are right or not. I don't think we will ever have to increase more than 31 times. Even this 31 will be when even this 31 case will come when I think B is equal to 1 or something. Maybe then also we don't need more than 30 or 29. But anyway, so we managed to do the first problem. Now let's see the second problem. So there are 600 submissions right now. Okay. Given a positive integer k, two arrays are called k similar if they are strictly increasing. Okay, so we need to strictly increasing arrays, and they should have the same length, and all their elements are positive even between 1 and k. Okay, and they differ in exactly one position. Okay, fine. So you are given an integer a and a strictly increasing array a and few queries. For each query, you are given two integers l and r. Okay, and your task is to find how many arrays b exist such that b is k similar to this thing. Okay. So we are in each query we are given a sub array or sub segment of the array, and we want to find how many arrays are k similar to the sub segment that we're given. Okay, so yeah, that's the question, and k is quite big, I think, but k is at least n, so this might be an important constraint here, although I'm not sure how that will help. But there is strictly increasing. Okay, right, yeah. So if it is strictly increasing, then obviously a has to be greater or equal to n. Otherwise, the answer will be 0. Like otherwise, you won't even get a strictly increasing array in general. Yeah. So we know that a is strictly increasing, and we want b. Okay, and you have a lot of queries. Okay, so let's see what it will be. So maybe this is the array, right? And let's say in a query you are given a certain subsegment. So corresponding to that, you want to make another array. Okay, and it has one element different and all the other elements are same. Maybe it's like, let's say all these elements are same, but this one element is different. Okay, and I think the range of this, oh wait a minute, they differ in exactly one position, right? Yeah, exactly one position. So this has to be different, this cannot be same. I think it is something like for this thing, let's say this element is x and this element is y. So this element should be strictly between x and y. So it should be, let's call this thing that we place here z. So z should be smaller than y and greater than x, right? And it should not be the original this thing. So let's say this was a original p originally. So z is not equal to p, something like this. So maybe we want the number of elements that are between y and x. So they are y minus x minus 1, right? These many elements, and we will also subtract 1 because this is not equal to this thing. So we get y minus x minus 2. Okay, so these many choices are there for this element, and maybe that's it. So we just take all x and y like this, and we add y minus x minus 2 to our answer. Okay, right, I think that's what we want to do, and maybe we can simplify this very easily because I can see that wait a minute, we have y minus x minus 2 here, but x will also be added to something like so it is like I have a3 minus a1 minus 2 or something like this. Then I also have a4 minus a2 minus 2. Then I also have a5 minus a3 minus 2, and then a6 minus a4 minus 2, and so on. Right, so we can see that these two terms are getting cancelled out. These two terms are also getting cancelled out, I think, and so on. So I think a lot of terms will get cancelled out. Only maybe the last two and the first two terms will remain, probably, right? Because if we had other elements, like if we had a7 minus a5 minus 2, so yeah, this would also get cancelled. Yeah, so maybe just the last two and the first two elements will remain, everything else will get cancelled out. Yeah, I think that's it. And how many times minus 2 do we have? Yeah, just this length of subarray minus 2. So maybe we have AR plus AR minus 1 minus AL plus 1 minus 2 times this number of elements minus 2, right? maybe this is R minus L minus 1, I think, right? If we had 5 elements, so we need wait a second, 1 and 5 it gives us 5, 4, no, maybe this is 2, I think. Between 1 and 5 we have 5 elements, right? And 5 minus 1 equals 4 minus 1, which is 2. Okay, yeah, which is 3. Okay, yeah, so this is correct. So this is what we will get in general, right? But we haven't considered the fact that the first and the last element could be different. Okay, we have to consider that as well. So what will happen if the first element is different? If the first element is different, maybe we have something like if AL is not the same, if it is different, we have something between AL plus 1 and 0 and 1. Okay, so from 1 till AL plus 1 we can place anything except AL plus 1 itself and except AL. Okay, so yeah, we will also add this thing, right? So when we add this thing to our answer, this gets removed and this gets removed. Okay, so it becomes something like maybe we erase this and we erase this. Sorry. Yeah. Okay, so we're left with this thing. Now we have to add the contribution of the rightmost. If we remove the rightmost, I think we add something like anything between K and AR, right? Yeah, AR minus 1. Okay, we have to put anything between K and AR minus 1. Just a second. Right, except the number that is already there. Maybe we have to add this to our answer. This will also get removed, and our answer will simply be K plus AR minus 1. Sorry, K plus AR minus AL minus 2 into R minus L minus 1. I think this is the answer in general. Let's see. 3, 4, right? Maybe just too thin of a gap. Let's see for this one, 1, 4. Okay, so the answer should be, I think, 7 minus 2, which is 5, plus or minus. Okay, minus 7 minus. Let's put it here. Okay, in this formula, if we put the values, we get, what is K, by the way? K is 10, right? Yeah. Okay, we get 10. I think this might not be visible here. Let me use some of this place. Okay. Right. So we put 10 plus 7 minus 2, I think, right? Minus 2 into R minus L, I think. Yeah, 4 minus 1. Minus 1. Okay. So the answer should be something like this is 15 minus 6 minus 1, which gives 8, right? 40 minus 8. Okay, is the answer 8? Okay, right. So it is 8. So I think this formula will always give us the correct answer. Maybe one exception is if L equals R, then what will happen? If L is equal to R, we get AR minus AL, which is 0. R minus L is also 0. Then K minus 1. I think this formula will always work. So we can try it, except if they are adjacent, maybe it won't work. Let's try for this case, 2, 3. So we have 5 plus 4, 9 minus 2, that is 7. 7 minus 2 is 5. 5 minus 1 is 4. Okay, yeah, so it's always working, I think. So we just have a simple formula here. Okay, we start from this. Now we need the array A, I think. Okay, we have nqk, right? Okay, q lines, and all of them have lr. So we take lr as input. Then maybe I should do r minus minus and l minus minus, because my array was one index. So I'll do it one index. Okay, that's fine. I can do something like I1 n plus 1 and input A, right? Okay, that's it. Now we have to just print the answer according to the formula. So answer is equal to k plus AR minus AL plus, sorry, minus 2 into R minus L minus 1. And then we can just print the answer, I think. We don't have multiple test cases, right? There's only one test case. Okay. It should be probably correct. I manually verified it on a lot of test cases. Yeah. Okay. So 30 minutes and we have done only 2 problems, but we started 15 minutes late, so I think that's okay. Okay, so yeah, we got 2 problems correct. And now we're at C. There are relatively less submissions till now, only 124. So by this, I can say maybe it will take me around 15 minutes to solve this problem. Yeah, because usually when I solve division 2C, there are 100 something submissions, right? And I started 15 minutes late, so I think it will take me 15 more minutes to solve this one. Okay, so I think probably by like when 1 hour and 30 minutes will be left, I would have submitted this probably. Okay. So pair of positive integers a comma b is special if, okay, so we are at problem C right now. This is floor and mod. Okay, so I think I can see floor, but I don't understand what's mod here. Then anyway, so a pair, okay, yeah, see the mod too. This is the mod. Okay, a pair of integers a comma b is special if a by b floor division is equal to a mod b. A by b floor equals a mod b. Okay, maybe the divisor equals remainder, right? Yeah, so yeah, sorry, the quotient and the remainder are same. Okay, yeah, that's what we want. And we want the number of special pairs a comma b such that a is in this range and b is in this range. Okay, okay, and we are given x and y. Right, so we want something like we have a and b in such a way that wait a minute. We want a to be equal to bk plus b, I think. No, 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 no. kb plus k, right? Yeah, probably this. We want a equal to kb plus k. See, now if we, and obviously k is smaller than b. So k is smaller than b and we want a equal to kb plus k. Maybe, yes, I think that's it. So now when you divide a by b, you get around k. You get k exactly, because like if you divide b from here, so this term gives you exactly k, and this becomes 0 because k is smaller than b. A by b equals k on flooring. Wait a minute. Yeah, on flooring this gives you k, and a mod b is definitely k because this term becomes 0, right? So it should be of this form, I think, and this can be simplified as b into k plus 1, I think. Sorry, k into b plus 1. Okay, so we want so when we choose a b, we want a to be in this range. Wait a minute. We choose a, sorry, let's say we choose b, and from that we can get a by doing k into b plus 1, right? If we have b, if we have already decided b, we can get a this way. Maybe this won't work for b equals 1. No, it would, yeah. You only get 0, but 0 is not in the range, so that's fine. Right, so it is something like if you choose b, k into b plus 1 is the thing you want, and k should be smaller than b, right? So how many numbers are there? I think just normally there should be b numbers like this, because this can be 0, 1, 2, 3 or anything. Anyway, k can be 0. Okay, no, k cannot be 0, right? Because if you put k equal to 0, a will be equal to 0, and a is at least 1, right? So k cannot be 0. It will be at least 1 or 2 or 3 or 4 till b minus 1. So there are b minus 1 such numbers, right? So there can be b minus 1 numbers like this for any b, but for some b's, I think b minus 1 into b plus 1 will be too big, and it will be bigger than your x which is given in the input, right? So we want the maximum k in such a way that that's not much. Yeah, okay. So is this like a is this like a square root decomposition kind of thing? Let me think. Yeah. Uh, let's see. So we have b and k into b plus 1, right? So till square root of like till some value till, let's say, square root of what? Yeah, let's say till 10 to the power 5 or something. Yeah. So till 10 to the power 5, maybe we can do this thing that we can iterate on the b, and we can see a by b plus 1, maybe this thing, to get the k. Okay, minimum of this or b minus 1, right? We can do this thing, and then for the other direction, for the b's which are greater than this thing, maybe we can iterate on this thing, because there are not a lot of values for this, and that way we can get the answer, maybe. Because I know that the total number of values of this are not much, right? When b plus 1 is around like when b plus 1 is smaller than root a, I can iterate on b, and when b plus 1 is greater than root a, I can iterate on this value, a by floor of a by b plus 1, something like this. I can do this thing, so that way I will be able to get the answer, right? That should work. Then I have to know for how many values I'm getting this thing. Yeah, so that's not very tough. Okay. Right. Wow. Okay. sorry, e plus 1 smaller than root a. I can have one algorithm, and for the other one I can have another algorithm. Right, one of them will always be smaller than root a. And a is of the form kb plus 1. Wait a minute, maybe a should be divisible by b plus 1. No, sorry, this is not a, this is x. This is x. Okay. Yeah, this is x. What's happening? Okay, yeah, so this is not a, this is x. Oh, sorry. You want the total number of pairs, right? I don't like this problem. Okay, but okay, fine. We have t test cases, then we have a and b. Okay, and then we have sorry, x and y. Okay, so we can iterate over. Wait a minute. Start from here. Okay, we want b. Like when we choose the b, we want a to be of the form a into b plus 1. Okay, we want to see how many multiples of b are there up till x, but this k should not be very big. It should be smaller than b minus 1, right? And that's it, I think. Right. So this is something like x by b plus 1. Uh, x by b plus 1, minimum of x by b plus 1, comma uh, b minus 1, right? This thing we want. The summation of this for all b. And we can iterate over b to get this, right? So let's try to write that before we write the square root decomposition. B starts from 1, goes up till y. Let's say our answer is initially 0, and we want to add to our answer minimum of x by b plus 1, comma b minus 1. This thing we want to add to our answer, and that's it, I think. So this answer will give us TLE, but let me see if it is correct. This is obviously, this will go till 10 to the power 9, but let's see. Okay, yeah, so it is correct. Now we just have to optimize this thing to run in a way that it does not give us TLE, right? So I know that the total number of values of this are not too much. So for a lot of values, it will be like when when x is when b plus 1 is greater than the square root of x, then this will be relevant. Otherwise, we can iterate over this value, which will be small, right? So we can maybe update this loop in that way. B plus 1 into b plus 1 is smaller equal to smaller than x, I think. Okay, so this is basically what we call square root decomposition. Right, so till b plus 1 is till the square root of x, we can do this thing, right? And for the other values, we can iterate over this value x by b plus 1. We can say for int x by b plus 1. Okay. Yeah, so what will be the minimum value of x by b plus 1? That is x by y plus 1, obviously. Okay. Obviously, and b is smaller or equal to y, right? So we start by this. This should be equal to x by b plus 1. Let me call it z. Okay. And we want this thing, we want z into z to be smaller or equal to x, I think, and z plus plus. Okay. Just normal square root decomposition. Yeah. Okay. Okay, so we start from here, we go till here, and so on. Okay. And now we want to add to our answer minimum of z comma b minus 1, I think. No, we don't know the b here, right? Maybe we can get it. No, wait a minute. We're iterating on x by b plus 1. Okay. Why am I stuck at this? It's not that difficult. Yeah, first of all, I think we need how many of them will give us this value z. We want how many b will give us this value z, right? So we want x by b plus 1 equal to z, right? And we want how many b's will satisfy this thing, right? Exactly. Should not be stuck at this thing. It's easy. I think I'll flip it again. X by b plus 1 equals z, right? And we want how many b's will give us this thing, right? Is it something around x by z or something related to that? If this floor wasn't here, we could have said something like x by z equals b plus 1, but we have this floor, right? So maybe we can say something like x by x by b plus 1 is greater than z. Yeah, that is correct. A little greater than z, greater equal to z actually. So x by z is greater equal to b plus 1, I think. Right. And that means b is smaller equal to x by z minus 1. Is that a useful information? By the way, this is a fractional value. If we subtract 1 from this, this is still a fractional value, but we want only integer values from b. Maybe, yeah, we had another equation that is x by b plus 1 is greater than z. This gives us x plus b plus 1 greater than z, and now we do the same thing again. We get b plus 1 is smaller than x plus b plus 1 by z, and we can subtract 1 from here. When we got b smaller than, this time it should be greater than, right? Yeah, b is greater than x plus b plus 1 by z, and we can subtract 1 here, right? So now we have a lower bound and upper bound both. X plus b plus 1 by z minus 1 should be smaller than b, which is smaller or equal to x by z minus 1. We can remove this minus 1 from both sides and we can just get the value of b plus 1 like this. So yeah, it is between x by z and greater than x plus b plus 1 by z, right? So how many numbers are greater than this but smaller than this, smaller or equal to this? Wow, okay. This should be very easy, I think. Mm, right. This thing we have. So I think it's just very few numbers between this range. Oh no, we have a b plus 1 there. What do we do with that? What am I doing? Wait a minute. We want to iterate on x by b plus 1 and we called it z. Now I want to know how many b's will give us this z, right? Mm, right. So x by capital B equals z. That means x by z equals b or something. Is that true? I think it's not true because z is a bit smaller, right? And what x by b should be. And then if we multiply and then if we divide, okay, we could have done binary search to get the smallest and the biggest one. 100 root n log n. Maybe we could binary search. Maybe we can binary search for b and find the smallest and the biggest b, which will give this thing. Okay. Okay, now if x by m plus 1 equals z, yeah, okay, if this is greater or equal to z, then we can say m is one of the answers, but we want even smaller, right? So we will say no. If we take this very small, then that will be very big. This value will be big if m is small. So if we want the smallest m, we want this to be smaller equal to, I think. Yeah. And now since we want the smallest m, we can say u equals m minus 1. Here we can say l equals m plus 1. So this way we get the smallest b such that it satisfies this thing. Now let's say the biggest b or as well. Again we put l comma u equal to 1 and y. Do this thing again. Probably binary search is an overkill here and not required, but anyway. So if this is greater or equal to z, that means that's fine. Big is one of the answer, but we want the biggest answer, so we'll do something like this. I think so. That's correct. If x is big, this will be very small, but this very small is still greater or equal to z. That is fine, but we will increase L even more, so that will be even smaller. Yeah, that's fine. So we have the smallest value of big and the biggest value of big. So we can say possible values of this will be big minus small plus 1. Right. Now we want to add this thing to our answer, I think. Z to our answer. Right. So we will say answer plus equals Z. And now there is one problem. What if Z is greater than B minus 1? X by B plus 1 is greater than B minus 1. This could be true, right? This will be true if uh, x is greater than b square minus 1, I think. Just transpose this here. How much time have I wasted on this? Has it been 20-30 minutes or something? Oh, 30 minutes. Wow, okay. What? How do I get this thing? Hmm. Okay, I have the small and the big, right? And if z is between them, then that's a problem, I think. Okay, so normally we would add answer into first to our answer. But if z is somewhere between small and big, then we have to do something else. Okay, let's see. This thing we will do if so till one value b minus 1 will be smaller, then they will be equal. After that, it will be greater. till z plus 1 we will add b minus 1, right? Till b equals z plus 1. Just a second. Oh my god. Maybe that case will never come because we had this thing or something like that, right? Mm-hmm. B plus 1 equals z plus 2. I think this is the case when z is smaller than b plus 1, right? We're talking about the case when z is smaller than b plus 1. So obviously z will be smaller than b minus 1, I think, right? Yeah, so we can take care of that. Maybe we just have to remove the equality from here, put it here instead. Now in this loop I can automatically say, so like in this loop, if we talk about this loop, we know that z is greater than b plus 1, okay, greater equal to b plus 1 in fact. In this one I think z is automatically smaller than b plus 1, right? So obviously z is smaller than b minus 1 as well. Maybe we can just add possible into z to our answer. No, that's incorrect. Hmm. Assert z is greater than, sorry, z is smaller than b minus 1. It's a minus 1. Oh, it failed. Okay. Maybe we should have started this in a way. We should not take this into consideration, right? Maybe we can start this from mxb plus 1, because till mxb we've already done it in the above loop. So this one we should start from mxb plus 1. Still wrong? No, wait. If z is smaller than b plus 1, z is smaller than b minus 1, what does this even mean? Obviously that's wrong. Okay, we can loop on two intervals. Maybe z is greater equal to b minus 1. And z is, here we want z is smaller than b minus 1. Yeah, I think that's fine. Still wrong. Why is this wrong? Hmm. Oh, sorry. Sorry. Hmm. I wanted x by b plus 1 to be greater equal to b minus 1. Right, so maybe I can multiply b plus 1 on both sides. Get x is greater equal to b minus 1 into b plus 1. Maybe a little more. Okay, right, so maybe when it never found an answer, it was still trying to do something with this. So yeah, that's why the assertion was failing. Maybe it's correct now. This is going till square root of x. I think this loop is going around till square root of x or something. And then this one is also going till square root of x, I think. Yeah. We could have started it from 1 only because this u is limited. Yeah. And here we're doing a binary search. Maybe this is around 30 operations. This is around square root loop, right? So around 3 into 10 to the power 4, I think. 4 into 10 to the power 4 into 30 into 2. So let's see. Okay. Around 4 into 10 to the power 4 into 30 into 2. Right, that's what we're doing. And 100 test cases. Is that 10 to the power 8 or something? Yeah, more than 10 to the power 8. Okay. Yeah, let's see. Let me try 64-bit compiler for this one. Prevent TL. Could be wrong answer as well. I mean, wow, it is passed. Okay, maybe it wouldn't have passed on the. So maybe I did it. I overcomplicated it a lot in the implementation. Like I was stuck with the implementation part, but let me explain the central logic behind this. Central logic was simple. It's something like A should be of the form KB plus K, right? Where K is smaller than B. Okay, so this was the central logic, and yeah, so you can write it as A equal to B into K plus 1, and you can yeah, so that's what we want. We want B comma B into K plus 1 all pairs. So what I did was I thought of iterating over on all B's, but Y is very big and B is in this range, right? So yeah, so B can be like B can take a lot of values, so you cannot iterate in this range. So what I did was, first of all, I iterated over this thing that wait a second. First of all, I think I iterated over B till square root of Y. I iterated over B, and after that I iterated over x by k plus 1. So after that I iterated over x by k plus 1. So this would run in square root of y time. And after that I got really confused with the implementation. Maybe I have never implemented this square root decomposition kind of thing earlier. I mean, I have done square root decomposition, but maybe usually we don't have to count the frequency or something. So I got a little confused with that. I had to use binary search for this one. And yeah, so that made it a bit slow because I had to use binary search here. I'm not sure how to do it in O1, but as far as I know, it's possible to do it in O1 to get the minimum and maximum in such a way that you get this thing. But I'm not sure how it's done. Anyway, so just 900 submissions. Okay, 900 is a lot, right? Anyway, we're at D now. Maybe this is even tougher or something. Yeah. Okay. You are given a matrix A consisting of positive integers. It has n rows, m columns. Consider a matrix B of consisting of positive integers. It should have the same size as A, and the following conditions should be met. So this is probably constructive algorithm. Okay. Okay. This is a range constraint on B. Then the element should be multiple. Okay, of those. Wow. What? Okay. 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 The difference between any adjacent pair of cells should be equal to k to the power 4 for some integer k. And k should be greater or equal to 1. Okay. Maybe this is one of the matrices that is given as input. 1, 2, 2, 3. Yes, we are given 1, 2, 2, 3, and we want to make another matrix from the multiples of this. And the difference between all adjacent cells should be some k to power 4, k greater or equal to 1. I think this is correct. The difference is 1, 1, 1, 1, and 1 is 1 to power 4. I think this itself is the answer here. Yeah. Okay, but this one is a problem. Okay, so we have. Is it always possible, by the way? Oh, okay, so it is always possible. Right, so here we have 16, 16, 16, 16, 16, 16. You want to construct a matrix from this in such a way that what? Right, so the differences are some k to power 4. Maybe we can just make 16a and 16b and so on. So we can make 16a. Okay, sorry. What? Yeah, okay. We can make 16a and 16b. And then again 16a, then again 16b, 16. What's wrong with this? Yeah, 16b and 16a and 16b and so on. This new driver update made this pen much worse actually. Yeah, I have to roll back the drivers after this. Anyway, so if we make it something like this, right? We want 16a minus 16b to be equal to some k to power 4. So it is like 16 into a minus b equals k to power 4. So I think a can be 2 and b can be 1, so this will work. So we just have 32, 16, 32, 16 and so on. Yeah, they have some 48s, but that's fine. We could have had 32, 16, 32, 16 and so on. But here is the real problem. How do we do this one? In general, we can start with something like 3a minus 11b is equal to some k to power 4. Isn't that very tough to solve? How can we get this thing? Some k to power 4, right? That's very tough, I think. Oh, hmm. Hmm. A is very small. Why is this very small? First of all, we have to see that the answer is always possible. So that is something. I'm pretty sure that this answer must be very misleading and there must be some easier answer here. I don't see how we can find this answer. It has to be misleading. Oh, right. I think I have one answer. So yeah, so I think I have a very cool answer. I think I have a very nice answer actually. So let's try to check. So I'm going to take the LCM of the first, like all the numbers between 1 till 16. Okay. So let's say the LCM equals 1. Okay. So till 16, I'm going to take the LCM of all the numbers. And LCM equals LCM into I divided by GCD of I into GCD of I comma LCM, right? Let's see the LCM of all the first n numbers, all the numbers from 1 till 16. Actually, this is not very big, right? LCM and 2 LCM, right? So let's print both LCM and 2 LCM, and they are both smaller than 10 to the power 6, I think. No, I think this one is bigger than 10 to the power. So that's problematic. Wow. Okay. Maybe if we didn't have 16, we could have done this. Like if we had till 15, it would have been easily possible. Yeah, see, if we had the numbers from 1 till 15, we could have done this one by just using. So we know that the LCM, I can think of one solution that could have worked till a smaller or equal to 15. So the LCM of all the numbers from 1 till 15 is equal to around 3 into 10 to the power 5, and its double is around 7 into 10 to the power 5. Right? So it is 3.6 into 10 to the power 5 or something. Anyway, so we could have just taken a matrix with L, 2L, L, 2L, and so on. No. That would that have worked? No, that wouldn't have worked. Why did I even think of this? Yeah, that probably wouldn't work. But if we have a number of the form k to power 4, and here also we have a number of the form k to power 4, right? And let's say these two numbers are equal. Okay, so let's say these two numbers are equal and both are of the form k to power 4. Then we can make it k to power 4 and 2k to power 4 and be done, right? But the problem is that this can work for two adjacent elements, but we have more elements here. So on. Why is this so small? Maybe there's another solution. Maybe one of the idea that I thought was somewhere along the lines of we place x comma 2x, right, adjacent, and x itself is a power of 4, right? X is itself a power of 4, and then the difference is the form of k to power 4, right? So how big is 16 to power 4? It is 2 to power 8, I think, right? So it's not very big. No, 2 to power 4 into 4, 2 to power 16, I think. How big is 2 to power 16? I think is it 6553536. 16-bit character stores that much. Yeah, that's right. It's 65536. So that's not very big. So any number to power 4 is not very big, but their difference won't be a power of 4, right? it will be something else. But okay, we get this result that any number to power 4 is not very big in this within this range. What about the LCMs? What can be the biggest LCM here? Biggest LCM. Maybe it can be around. No, it can be very big. Let's take the product of all the prime numbers in this range. They are 2 into 3 into 5 into 7 into 11 and 13. Yeah, that's it. Which is a lot. 3 into a 4, right? Yeah, that's a lot. And why am I doing this? We can show that the answer always exists. Yeah, if I can do that too, then maybe I'll be able to print the answer. This is most probably a very misleading answer. Shouldn't care about this one. Bi is a multiple. This has something to do with choosing a multiple that is so big that we don't have to care about the other things. We can raise any number in the original matrix to power 4, and that won't be a problem. But how will that be helpful? Let's say we have a to power 4 and b to power 4. Can we multiply some constant here such that this is helpful? What? I think it's the opposite of helpful because we can never have a to power 4 plus k to power 4 equal to b to power 4 according to Fermat's last theorem. So this is always impossible. But with some constants getting multiplied to this, maybe it is possible. What about, do we even have to do this thing? A to power 4 and b to power 4. Let's start with one. Let's start with something relatively simpler. So we have x and y, or let's say x and x plus k to power 4, right? And x is a multiple of this, y x plus k to power 4 is a multiple of something else. Does it not have to do anything with the LCM? LCM is the common multiple of everything. We could have had Like if we make most of the elements equal to the LCM, right? Then what will we have here? LCM plus the number to power 4 maybe? No, no. Yeah, I think that will work, right? Yeah, I think this can work. So we can have LCM plus a to power 4, then again LCM, and then here we can have LCM plus whatever number there here it is. Like this is 2 and this is a12 to power 4. Then again we can have the LCM here. Then here we can have LCM plus a3 1 sorry 3 2 to power 4, right? And these numbers are not very big, so they can be only 65536. And LCM is also not very big, so it is around 7 lakh or something. Lakh, by the way, lakh means 7 into 10 to the power 5. Sorry, lakh means 1. What is this? What have I done? Whatever that was. Yeah. Anyway, so LCM is around 7 into 10 to the power 5, and the elements to power 4 are around 65536. If we add them, that's not a problem. Okay, so I found the answer. Oh no, I need the LCM, I think. Yeah. So I have the LCM of all the numbers, and I'll make the matrix in a way that the like it will be like a chessboard, and all the black elements are the LCM, and all the white elements are the LCM plus the original number plus whatever the power 4 or something. Anyway. Okay. Yeah, we don't even need a matrix for this. We can just print the answer directly. Okay. Let's say I take X as input. Okay. And I just have to see if I plus J is even. Okay. So let's say if this is even, or let's say if it is odd, then I will print LCM. Okay. Otherwise, I will print LCM plus X to power 4. Right. After this, I just leave a line. And there we go. Done. Sorry, yeah, this is 17. Yeah, so we've done everything. Okay, yeah, it's done. Okay, so this was actually a very nice question, and yeah, this was very nice. Okay, so let me explain the solution. This was actually very interesting. So what we did was we know that LCM will divide all the numbers. So like first of all, I found the LCM of the numbers from 1 to 16. You can see the part in which I was thinking about it. Why I thought about the LCM, because I knew that it has something to do with so small a's. I knew that something will be small, so yeah, LCM is small. So the LCM is around 7 into 10 to the power 5. Okay, yeah, the LCM is not very big, and I know that all the numbers are like LCM is the multiple of all the numbers, right? So if I place in the matrix L L L L L L L, it is fine. All the numbers are the LCM. Sorry, all the numbers like this LCM is the multiple of the original matrix. Like all the numbers in this matrix are the multiples of the original one, but we don't satisfy the plus k to power 4 condition, right? So what I will do is I have to add something to this element such that the difference between the these elements is something to power 4, and this is still the multiple of the original value. So let's say the original value was x, so I will add x to power 4 here. Here also I will add y to power 4, here I will add z to power 4, and so on, right? So you can see grids are usually bipartite. This means that uh, like we can color it like a chessboard, so all of these can be black, right, and all of these can be white. So what I did was, in the black cells I put just the LCM, and in the white cells I put LCM plus the original number to power 4, right? So I didn't even need to take the full matrix in input, like I didn't even need to store the matrix. What I did was, first I find the LCM, then I take n and m as input, then I take the number as input. So if it is a black square, I'll place LCM, and if it is a white square, I'll place LCM plus x to power 4, and that's it. Yeah, so this was a nice problem. So we have 23 minutes, and maybe we can look at F. Now I should probably stop this video because there are not many submissions here, so maybe I won't be able to do this. But let's see. So you are given an array of integers b1 till bn, and this is hybrid. Okay, okay. Copy or prefix sum, right? So the element is either the copy or the prefix. Find the number of hybrid arrays. What? Why is this not just 2 to the power n? Oh, sorry. Oh, right. Yeah. Bi is the hybrid. Okay, fine. I thought I thought the opposite. I thought that this is A and this is B. Okay, so we have something like sorry, yeah, we have something like we can either have the same element there in the other array, or Bi could be the prefix sum of all the elements that we have placed till now, right? Okay, so what's wrong with having 2 to power n? Like, what's wrong with 2 to power n? Why is 2 to power n, 2 to power n not an answer, not the answer? Is the answer not 2 to power n? Like here we can have 2 to power 8, I think. Oh, it's not. 2 to power 3, 2 to power 3, 8. What? Only 3 arrays? Like for each index we can choose whether this is a prefix sum. Like for each index of B we can choose whether this is this or that. And we can always make an array like that, right? So if we choose this, we have to copy. If we choose this, we can get the value of AI based on that. Maybe it will repeat. Yeah, that's the problem. We have 1 minus 1 1, right? So let's say everything is copy. We get this array. Let's say all of them are prefix sum. So maybe we get, okay, so let's say first is prefix sum and the others are copy. So again we get the same thing. Yeah, we have to remove the duplicates. Okay, so that's very complex, I think. What do we do here? Wow, I'm really clueless in this entire contest. Like most of the times I'm like, what to do? Although I did manage to solve 4 of the problems, but still, I think B onwards or something, I was very clueless about what to do. I think it's not my day. I even started late or something. Hmm. Hmm. Okay. Yeah. By the way, I wasn't cheating. I was just checking some college messages. Yeah. So, yeah, regarding the USP of my channel. Yeah. So I think the USP of my channel is that I do everything in dark mode. So even my Codeforces is in dark mode. My Sublime text is in dark mode. My drawing pad is in dark mode and everything. Yeah. So if you want to watch my videos in low light, I think I'm the best channel out there. Unless somebody else also does everything in dark mode. Like I know most of the YouTubers use dark theme IDE, but like I know some that use light theme as well. But I don't think anybody uses Codeforces as dark theme. Yeah. Anyway, so yeah, I know a lot of people will start asking me in the comments how to get this dark mode. So let me tell you already. I have this extension called Dark Reader. You can get it from Chrome Web Store or whatever. That way you can get dark. You just have to print. You just have to press Alt Shift and D, and it switches the dark and light mode. Okay. Also regarding the Sublime text setup, yeah, I can show you a little bit about how it works. So I have this. Right. So I have this Node.js file somewhere in my computer. This thing looks something like this. Oh, sorry. Uh, like this. Yeah, so I have this Node.js file that I've written on my own, and like not the entire thing. Maybe I've written this or something like this. This part maybe I've written, and I don't know how this works. I don't know how to get it work for you guys. Maybe you will have to change this part to your path, whatever it is, right? And yeah, so I use this command prompt to run this Node.js file, and it is just listening to port 12345 to the competitive companion, basically, which is another uh, plugin for Google Chrome that I have. So in that you can see I have the custom port 12345 here. So basically, when I press Control Shift U, uh, it reads the test case from this file, from this page, and sends it on the server 12345, and this listens to that port, so it reads that, and yeah, and it stores it to my this file on the desktop. Where is it? Yocpp.out. Yocpp.tests. It was somewhere here. I have a file name yocpp __ tests. I can't find it right now, but I have a file like that. Yeah, so in that all the tests are stored, and it fetches those from there. Wait a minute, did it not work this time? Yeah, I think it didn't work. Let me try to run this again. Maybe I tried to run the index.js file, that's why it didn't. Yeah, I think now it will work. Yeah, so it just read the test case, and we have a loaded here. That means it loaded it, and it saved it to this file, I think. Yeah, where is that file? CPP text. Maybe that's hidden or something. Anyway, so maybe let's try to run this. Maybe I will get the new test cases here. Yeah, so you can see I have the new test cases here. There is actually a file named yocpp test somewhere on my desktop. Should be here. Yeah, see yocpp test. Where was it? Yeah, okay, so sorry, yeah, this file. So yeah, these are the test cases, and they are read by this extension that I have. Where is it? Yeah, CPP Fast Olympic Coding. So that works with, you can press Ctrl Shift P and type install package. Then it will give you a list of all the packages that are available. From that you can choose CPP Fast Olympic Coding. Fast Olympic Coding. Okay, it should be here, but I can't see it because I already have that extension. Wait a second. Let me list the packages. Yeah, CPP Fast Olympic Coding. So if you have this thing, then it will be available to you. I'll probably put this file. Where did it go? Yeah, so I'll probably put this file into GitHub or something, and then give it to you guys so you can have it on your own. But yeah, so that's how I import my test cases or whatever. People keep asking me that a lot, how I auto import the test cases. So yeah, it's a long process for setting up, but using it is not that difficult. Like all I have to do is I have to just press Ctrl Shift U, and then it reads the, you can see the blue bar here. Yeah, so it reads the test case and broadcasts it on the server, on my local server within the computer. And this file, this node.js file, reads that test case, and upon reading that test case, what it does, it writes it into this file yocpp text, which can be read by my Sublime text using this extension Fast Olympic Coding. Yeah, so that's what it is. Also regarding this problem, not sure how we can get rid of the duplicates. But like I know it is 2 to power n, but there are a lot of duplicates there. I don't know how to get rid of those duplicates, which are a lot, by the way. Maybe we need the total number of distinct values of the prefix sum. No, not that. The indices at which it will differ, it will be equal to the prefix sum, right? Is it DP or something? Like we can, if we know till 1 point, how many they can make. will that determine for the rest? I think it also depends on what the prefix sum is till now, right? So yeah, I think that's very difficult. Has anybody done it? I mean, obviously people have done it, but 155 and E I haven't even read till now. Maybe I should stop this video here because I don't think I can solve this one. So yeah, thank you for watching.